In this video, we're going to see the two most important theorems in duality theory. These are strong duality and complementary slackness. The first result that we prove is weak duality. This result essentially shows that the motivation that we saw in section 4.1 is indeed correct. This theorem essentially says that the cost of any dual solution provides a lower bound for the optimal cost. Let's read the formal statement and then let's prove this result. If X is a feasible solution to the primal problem and P is a feasible solution to the dual problem, then we have that P transpose B is less than or equal to C transpose X. Now let's prove weak duality. As in the statement of the theorem, let X be primal feasible and P dual feasible. We need to show that P transpose B is less than or equal than C transpose X. So we show C transpose X minus P transpose B greater than or equal to 0. Of course, they're equivalent. So let's write down C transpose X minus P transpose B. By adding and removing P transpose AX, we obtain P transposed AX minus P transposed B plus C transpose X minus P transposed AX. Now we can factor out P transpose from the first sum, and we obtain P transpose AX minus B. From the second parenthesis, we can factor out instead X, so we obtain C transpose minus P transpose A times X. Now I'm going to define a vector u and a vector v such that this is equal to the sum over I of ui plus the sum over j of the vj. So where ui is defined as the pi times ai transpose x minus bi for every I, and the vj is defined as c j minus p transposed aj times xj, again for every j. Of course, to show that c transpose x minus p transpose b is greater than or equal to 0, we just need to prove that u and v are both greater than or equal to 0. In fact, if we do so, then this sum is greater than or equal to 0, and this sum is also greater than or equal to 0. Therefore, C transpose X minus P transpose B is also greater than or equal to 0. To prove that U and V are greater than or equal to 0, we only need to look at the definition of the dual. The definition of the dual implies, so first, Pi and AI transposed X minus Pi have the same sign. If they're both different from 0. Therefore, u is greater than or equal to 0. In fact, from the definition of the dual, we have that if AI transpose X is greater than or equal to Pi, then Pi is greater than or equal to 0. Vice versa, if AI transpose X is less than or equal to Pi, then in the dual, Pi is less than or equal to 0. Finally, if AI transpose X is equal to Pi, then the second quantity is 0. Similarly, from the definition of the dual, we have that Cj minus P transposed Aj and Xj have the same sign. And this implies that V is greater than or equal to 0. And this concludes the proof of weak duality. Before proceeding, I want to give you a geometric view of the weak duality theorem. Let's say we have a primal problem where we minimize C transpose X subject to AX greater than or equal to B and X free. I visualize the set of feasible solutions below here with this polytope P. Then the dual takes the form maximize P transpose B subject to P non-negative and P transpose A equal to C transposed. Now let's pick a dual feasible point and we call it P bar. From weak duality, we know that C transposed X is greater than or equal to P bar transpose B for every feasible X. Now we can use the equality constraints in the dual to replace C transposed X with P bar transposed A X. So we have obtained that P bar transposed A X is greater than or equal to P bar transpose B. So our dual feasible P bar gives us an inequality involving the variables x, therefore an inequality for the primal problem. My goal in this slide is to visualize this inequality. The only thing that I need to visualize this inequality is to use again weak duality with the vector x star that is optimal for the primal. So I obtain that C transpose x star is greater than or equal to P bar transpose B. So at this point I can nicely visualize my inequality obtained from the dual vector P bar. Let me start by looking at the optimal solution for the primal x star. Then we can draw the inequality C transpose x greater than or equal to C transpose x star. Since C is the cost function of the primal and x star is an optimal solution to the primal, then this inequality will be valid for my polyhedron. And of course, the vector x star will satisfy this inequality at equality. Now I can also visualize the inequality that we obtained from the dual vector p bar. Now the left-hand side, p bar transposed A x, is equal to C transposed x, as we already saw using the equalities in the dual. In this picture, this tells me that this new inequality is parallel to the inequality C transpose x greater than or equal to C transpose x star. So to understand the relative position of the two inequalities, I need to look at the right-hand sides. And the relationship between the two right-hand sides is given by the inequality C transpose x star greater than or equal to P bar transpose B. So this tells me that my new inequality is weaker than the previous one. Since the previous one was valid for my polyhedron P, then so is the new one. So the overall message of this slide is that using a feasible dual vector P bar, we can obtain an inequality for the primal problem, which is valid for all the feasible points of the primal problem, and whose left-hand side is C transposed X. From the weak duality theorem, we can derive some very interesting corollaries that provide us with some useful information about the relation between the primal and the dual. Let's start with corollary 4.1. This corollary tells me two things. First, if the optimal cost in the primal is minus infinity, then the dual problem must be infeasible. Vice versa, if the optimal cost in the dual is a plus infinity, then the primal problem must be infeasible. Let's now prove this corollary. Let's start with the proof of A. We assume that the optimal cost in the primal is minus infinity. We prove this statement by contradiction. So suppose, for a contradiction, that the dual has a feasible solution. Let's call it P. Now let's compare the costs of the primal with the cost of the dual. Since the optimal cost in the primal is minus infinity, there exists a primal feasible solution X with cost as low as we want, in particular with cost lower than P transpose B. So with P transpose B strictly larger than C transpose X. But this immediately contradicts a weak duality. However, by weak duality, we have P transpose B less than or equal to C transpose X. We have found a contradiction, hence the dual cannot have a feasible solution. This concludes the proof of A. Now the proof of B follows with a symmetrical argument. I suggest that you take the time to fully write down the proof of part B, and this will conclude the proof of corollary 4.1. Now let's see an example of the corollary that we have just proven. Let's say that in the primal we minimize x1 subject to x1 less than or equal to 1. Clearly, the optimal cost of the primal is minus infinity. If we write down the dual, we obtain maximize P1 subject to P1 less than or equal to 0 and P1 equal to 1. Clearly, the feasible region to the dual problem is empty, and so the dual is infeasible. Now let's see another interesting corollary of the weak duality theorem. Let X be a feasible solution to the primal, and let P be a feasible solution to the dual. Furthermore, suppose that the cost of the two solutions coincides. Namely, P transpose B is equal to C transpose X. Then X is an optimal solution to the primal, and P is an optimal solution to the dual. This corollary is extremely useful, and we will use it several times from now on. In fact, think about a situation where you have a linear programming problem where for some reason you have a solution that you believe is optimal. However, so far, if you wanted to prove to me that this solution is indeed optimal, this is not easy. One way to do this, for example, would be to run the simplex algorithm, starting from that solution, and use the simplex to show that it is indeed optimal. Another way to do that would be with our old optimality conditions. However, if you also construct a dual of your linear programming problem, and for some reason you also have a solution that you believe is optimal for the dual, then you can immediately convince me that your solutions are primal and dual optimal. In fact, I just need to check that they are primal and dual feasible, and this is very easy and quick to do, and then I only need to check that they have the same costs. If this is the case, this corollary immediately implies that your solutions are primal and dual optimal. Now let's see how we can prove this corollary. Let X and P be as in the statement. We start by applying a weak duality to any primal feasible Y and the dual solution P. For every primal feasible Y, weak duality yields P transpose B less than or equal to C transpose Y. But from our assumptions, we know that P transpose B is equal to C transpose X. So the cost of X is less than or equal to the cost of Y for any primal feasible Y. This means that X is optimal. To prove that P is optimal to the dual, we use a symmetric argument. For every dual feasible Q, weak duality, yields Q transpose B less than or equal to C transpose X. But once again, C transpose X is equal to P transpose B. So we have obtained that P transpose B is greater than or equal to Q transpose B for any dual feasible Q. This proves that P is optimal. This concludes the proof of corollary 4.2. Let's now get back to the slides. Once again, the corollary that we have just shown says that if you have a primal and dual feasible solutions with the same cost, then your two solutions are also optimal. The next results that we're gonna see is called strong duality. Essentially, it says that you are always in a position to use this corollary. In particular, it implies that if you have X optimal for the primal and P optimal for the dual, then they must have the same cost. Now let's see the statement of strong duality. If a linear programming problem has an optimal solution, so does its dual, and the respective optimal costs are equal. Now let's prove our strong duality theorem. In order to prove strong duality, we're gonna use two separate steps. In the first one, we're gonna use the simplex method. And in order to use it, we need to assume that our linear programming problem is in standard form, that there exists an optimal solution, and that the rows of A are linearly independent. Then, in the second step, we're gonna prove it for any linear programming problem by transforming it to an equivalent problem with the properties that we have just discussed. So first, we show the theorem for a linear programming problem in standard form such that there exists an optimal solution and the rows of A are linearly independent. Now let's write down our primal problem, which is min C transpose X subject to AX equal to B, X greater than or equal to 0, and our dual problem, which is max P transpose B subject to P transpose A less than or equal to C transpose. Next, we apply the simplex method. With the pivoting rule, that avoids cycling. At termination, we have an optimal solution let's call it X, and an optimal basis B. So at termination, all the reduced costs must be non-negative. Now the reduced costs, C bar, are defined as C transpose minus P transpose A, and they're greater than or equal to 0, where, as usual, P transpose is defined as C B transpose B inverse. Now the fact that P satisfies C transpose minus P transpose A greater than or equal to 0 exactly means that P is a feasible solution to the dual. In addition, let's look at the cost of P. P transpose B is equal to, we now replace P using this equality and we obtain CB transpose B inverse B. Now we know that B inverse B is equal to XB. So this is equal to CB transpose times XB. And this is equal to C transpose X. Now we're in a position to use our corollary 4.2 and obtain that P is an optimal solution to the dual. Corollary 4.2 implies that P is an optimal solution to the dual. And the optimal dual cost is equal to the optimal primal cost. And this concludes our first part of the proof. Thus, the theorem holds for LP problems in standard form that satisfy our assumptions. Let's now change page and prove the second part. Consider now a general LP problem, pi1, that has an optimal solution as stated in the statement. We transform this problem into an equivalent standard form problem let's call it pi2, in which the rows of the matrix A are linearly independent. We know that we can always reduce ourselves to this setting by dropping redundant constraints. So let me visualize our situation in a small picture. Let's say we have our original problem pi1 and our new problem pi2. We have obtained pi2 starting from pi1, and we know that these two problems are equivalent. Now let d1 and d2 be the duals of pi1 and of pi2, respectively. In our picture, we're going to have d1 here and d2 here. We now apply Theorem 4.2. This theorem says that since pi1 and pi2 are equivalent, then also their duals d1 and d2 are equivalent. by Theorem 4.2, D1 and D2 are equivalent. So I'm going to put a link here and I'm going to write EQ just to remember that they are equivalent. Now in the first part of our proof, we have already shown that pi2 and d2 have the same optimal cost. We have already proven that pi2 and d2 have the same optimal cost. In our picture, I'm going to put a link between pi2 and d2 and write same optimal cost. Now we're almost done. We want to show that pi1 and d1 have the same optimal cost. Now we know that pi1 has the same optimal cost as pi2 because they're equivalent. Now pi2 has the same optimal cost of d2, and finally we know that d2 has the same optimal cost as d1 because they are equivalent. So we have obtained that pi1 and d1 have the same optimal cost. And this concludes our proof of strong duality. Let's get back to the slides. As you saw in our proof of strong duality, we used the simplex method. It is interesting to know that there are different proofs of strong duality that don't use the simplex method at all, and you can find one in the book. Now let me get back to the geometric view of the duality theorem that we already discussed after weak duality. If you remember, we saw that any feasible solution to the dual gives rise to an inequality in the primal space. Such an inequality is valid for the feasible region P of the primal problem and is parallel to the inequality C transpose X greater than or equal to C transpose X star, where X star is an optimal solution for the primal. Now in the same argument we can use a strong duality and obtain that P star transpose B is equal to C transpose X star, where now P star is not only feasible for the dual but also optimal. This implies that the inequality for the primal problem obtained using P star, which is P star transpose A times X greater than or equal to P star transpose B, exactly coincides with the inequality C transpose X greater than or equal to C transpose X star. This is how we can visualize geometrically that the optimal dual solution gives me the best lower bound for the primal problem. Now, thanks to the duality theorems, we can nicely categorize our linear programming problems in terms of the possible outcomes of the primal and the dual. Recall that for every linear programming problem there are three possibilities. Either there is an optimal solution, or the problem is unbounded, or the problem is infeasible. So far, we've only discussed the unbounded problems for a problem in minimization form. And this exactly meant that the optimal cost is minus infinity. Symmetrically, if we're talking about a maximization problem, like the dual, then the problem is said to be unbounded if the optimal cost is plus infinity. So we have three possible outcomes for the primal and three possible outcomes for the dual. So in total we have 9 possible outcomes that we can visualize in this table. Here it doesn't really matter which one is the primal and which one is the dual. Each one can have a finite optimum, or it can be unbounded, or it can be infeasible. The first thing we should observe is that strong duality immediately rules out 4 of these possible outcomes. In fact, the strong duality theorem says that if one problem has an optimal solution, then so does the other. So if we look at the first column, this problem has a finite optimum, and so the other problem cannot be unbounded or infeasible. Similarly, if we look at the first row, we can say that these two outcomes are impossible. Using corollary 4.1, we can also rule out the case where both problems are unbounded. In fact, this corollary implies that if one problem is unbounded, then the other must be infeasible. We are left with 4 possible outcomes. Both problems have a finite optimum, both problems are infeasible, or one problem is unbounded and the other infeasible. So far we have seen examples of almost all of these outcomes. The only one we've never discussed is the case where both problems are infeasible. So let's see a quick example to convince ourselves that this can indeed happen. Let's say that our primal problem is the problem of minimizing x1 plus 2x2 subject to x1 plus x2 equal to 1 and 2x1 plus 2x2 equal to 3. Clearly this problem is infeasible, because if x1 plus x2 is equal to 1, then 2x1 plus 2x2 is equal to 2 and not 3. If we write down the dual problem, we obtain the problem of maximizing p1 plus 3p2 subject to p1 plus 2p2 equal to 1 and p1 plus 2p2 equal to 2. Of course, the two equality constraints contradict each other, and so the dual problem is also infeasible. In the assignment, you will see Clark's theorem. Clark's theorem discusses another interesting relation between the primal and the dual. It says that either both problems are infeasible, or at least one of them must have an unbounded feasible set. Next, we're going to discuss complementary slackness. Complementary slackness, in a sense, is equivalent to strong duality, and will provide us with some very useful tricks. Let's immediately see the statement of the complementary slackness theorem. Let x and p be feasible solutions to the primal and the dual problem respectively. Then the vectors x and p are also optimal if and only if these conditions hold. These conditions are called the complementary slackness conditions, and they say that for every dual variable, the product between this variable and the slack of the corresponding primal constraint is equal to 0. The second condition says that for every primal variable xj, the product of this variable with the slack of the corresponding dual constraint is equal to 0. For now, let's focus on the first condition. The first thing to notice is that this is a nonlinear equation. In fact, we have the dual variables p that multiply the primal variables x. Next, we should observe that this product between pi and the slack of the primal constraint can be equal to 0 if and only if at least one of the two factors is equal to 0. Of course, the same observations hold for the second constraint, which is in a sense symmetric to the first one. In particular, similarly to corollary 4.2, this theorem allows us to prove that two feasible solutions x and p are optimal. This, of course, is only the direction from right to left of this if and only if. In this case, to prove that x and p are optimal, we need to check that they are feasible and that they satisfy the complementary slackness conditions. Now let's prove the complementary slackness theorem. In the proof of complementary slackness, we will use some things that we've already observed in the proof of weak duality. So, in the proof of weak duality, we showed that C transpose X minus P transpose B is equal to the sum of Ui over I plus the sum of Vj over J, where Ui was defined as Pi times AI transpose X minus Bi, and Vj is equal to Cj minus P transpose Aj times Xj. So, surprise, surprise, the two products that we have in our complementary slackness conditions exactly coincides with our definitions of UI and VJs in the proof of weak duality. In the proof of weak duality, we also noted something else. We also noted that for x primal feasible and p dual feasible, we have ui greater than or equal to 0 for every I, and vj greater than or equal to 0 for every j. At this point, we're essentially done. So now let's prove the two directions of the if and only if in the complementary slackness theorem. First, assume that x and p are optimal. So if x and p are optimal, then we know by strong duality that their costs coincide. So the difference here is equal to 0, and since all the ui's and the vj's are greater than or equal to 0, this implies that all the ui's and all the vj's are 0. Then ui equal to vj equal to 0 for all ij. So we have shown the implication left to right in the statement. Let's now prove the converse implication from right to left. Conversely, if ui equal to vj equal to 0 for every ij, then, again by looking at the equality in the second line of the proof, we obtain that C transpose X is equal to P transpose B. Now we can use corollary 4.2, which implies that X and P are optimal. This concludes the implication from right to left, and so we have shown our complementary slackness theorem. In the remainder of the video, we will discuss some consequences of our complementary slackness theorem. The first thing to notice is that if our primal problem is in standard form, then the first type of complementary slackness conditions are always satisfied by every feasible solution. This is because having equality constraints in the primal implies that every feasible solution satisfies AIX equal to BI, so the product will be automatically 0 because the second term is 0. So now let's consider instead the case where our primal problem is not in standard form and also has a constraint of the form AI transpose X greater than or equal to BI. Then the corresponding complementary slackness condition says that if the constraint is not active, we need to have the corresponding dual variable pi equal to 0. And this fact has a clear geometric explanation. First, note that setting pi to be equal to 0 means that we're not using the corresponding primal constraint to obtain a lower bound. So our complementary slackness condition tells us that we don't need to use such a constraint to obtain the optimal lower bound, which is the highest lower bound. This implies that if we have a constraint that is not active at an optimal solution, then we can remove such an inequality from the problem without affecting the optimal cost. And this is because once we have removed such an inequality from the primal, then we can still obtain the same optimal dual bound. So the optimal cost doesn't change. This situation is visualized here in the picture on the right. Let's say that our feasible region is the polytope P, and our optimal solution is the vertex down here. This inequality in the top left of the picture is not active at an optimal solution. So we have just understood that we can remove this inequality without affecting the optimal cost. In fact, if we remove this inequality from the problem, then the new feasible region is this larger polytope P'. In particular, P prime is a triangle that contains the original feasible region P. As you can see, the optimal cost doesn't change because the old optimal solution is still optimal. Now we go back to consider a primal problem in standard form. We're going to assume that a non-degenerate optimal basic feasible solution is known, and we will see how the complementary slackness conditions can be used to determine a unique feasible solution to the dual problem. We will then see that this dual solution is also optimal. To understand this behavior, we first look at an example. Here we have our primal linear programming problem on the left and the corresponding dual problem on the right. I immediately give you out of the hat an optimal solution x star for the primal. Of course, at this point you don't have a quick way of verifying that x star is indeed optimal. However, you can easily check that the vector x star is a non-degenerate basic feasible solution. Also, you can immediately compute its cost, which is 19. Now let's consider the complementary slackness conditions. Since the primal is in standard form, the first type of complementary slackness conditions are automatically satisfied since x star is feasible. So now let's look at the second type of complementary slackness conditions. These conditions say that Cj minus P transpose Aj times xj star is equal to 0 for every j equal to 1, 2, and 3. This condition is clearly satisfied for j equal to 2 because we know that the second component of x star is already equal to 0. On the other hand, the first and third components of x star are strictly positive. Therefore, the complementary slackness condition implies that the first factor is equal to 0. So we obtain that the first and third constraints of the dual must be satisfied at equality. If we write it down, we have 5p1 plus 3p2 is equal to 13 and 3p1 is equal to 6. This is a system of two linearly independent equations in two variables, and you can easily check that the unique solution is p1 equal to 2 and p2 is equal to 1. So as promised, we use the complementary slackness conditions to determine a unique solution to the dual. The solution for the dual that we obtained, which is 2, 1, is dual feasible. In fact, we already know that it satisfies the first and third inequality constraints, so we only need to check that it satisfies the second one, and it does. Then, if you calculate the cost of our dual solution, you will find out that the cost is 19. And if you remember, this is the same as the cost of x star. So at this point, we have a feasible solution to the primal and a feasible solution to the dual with the same cost. We can use our corollary 4.2 and obtain that both our solutions are actually optimal. At the beginning of the example, I told you that x star was optimal, and now finally we have shown it. On top of that, we have shown that the solution 2-1 is an optimal solution of the dual. So once again, as promised before this example, the unique optimal solution for the dual that we obtained is also an optimal solution. Now that we've understood how things work out in an example, let's prove this in general. So we suppose that X is a non-degenerate optimal basic feasible solution to a primal problem in standard form. Let's now look at the basic variable xj. Since x is non-degenerate, we have that xj is strictly positive. So we look at the corresponding complementary slackness condition. Since xj is positive, we need to have that P transpose Aj is equal to Cj. We obtain such an equality constraint for every basic variable. So we can rearrange all these equality constraints in matrix form using our basis matrix, and we obtain P transpose B is equal to CB transposed. Now, since the matrix B is invertible, this system of equations has a unique solution, and this can be found by multiplying on the right by B inverse. So we obtain the dual solution P transposed equal to CB transposed B inverse. So in this slide, we have seen how, under our assumptions, we can obtain a unique solution to the dual. We still have to show that it's feasible and optimal. To do so, we use the fact that the reduced costs are greater than or equal to 0. And this holds because our primal solution is optimal and non-degenerate. Now if we write our definition of reduced costs, we obtain that C transpose minus CB B inverse A is greater than or equal to 0, and in this formula we have CB transposed B inverse, which is exactly the transpose of our dual solution that we just obtained. So we can write that C transpose minus P transpose A is greater than or equal to 0. These are exactly the constraints of our dual problem. So we have shown that the solution P is dual feasible. At this point, we have not only shown that P is dual feasible, we have also shown that it's an optimal dual solution. In fact, we have been enforcing the complementary slackness conditions with the optimal solution to the primal. So we have now shown that the unique solution that we obtain using the complementary slackness conditions is also optimal for the dual. In fact, if we look closely at the proof that we've just seen, we can see that asking the reduced costs to be non-negative is equivalent to dual feasibility. Now let's see an example where the reduced costs are not non-negative. And to do so, we just need to look again at our example 4.6 and pick a non-optimal basic feasible solution. In our previous argument, we also had the assumption that the solution was non-degenerate, and here we keep that assumption, and so we pick a non-degenerate, non-optimal basic feasible solution. An example of such a solution is x star equal to 0, 3, and 5 divided by 3. The cost of such a solution is 40. Now we can still follow the same line of thought as in the previous slides. So we can use the complementary slackness conditions to construct a basic solution to the dual. Now the positive components of x star are the second and the third. So we obtain that the second and third dual constraints must be satisfied at equality. We obtain the system P1 plus P2 equal to 10 and the 3P1 equal to 6. This system has a unique solution which is P equal to 2, 8. Now you can easily check that this solution is not dual feasible. In fact, if you substitute in the first dual constraint, you obtain a left-hand side which is 34, which is strictly larger than 13. So as expected, starting from a basic feasible solution to the primal, whose reduced costs are not all non-negative, we obtain the basic solution for the dual, which is not feasible. And this concludes our discussion about complementary slackness.